Hey grade 12s and welcome to this video. So in this video we are going to be working on the Euclidean geometry section of this paper. So this is the last video for this particular paper. Okay, so we're on question 8 and question 8 says, in the diagram below, P, Q, R and S are points on a circle with the center O. So those are just the points that you have on the circle. Then they tell us that OT bisects chord QR at T, and they also tell us that XRY is a tangent to the circle at the point R. Then OZ is produced to meet at Y, where OY is parallel to QR. So that is a very important thing to look at there. Then ROY, ROY, that angle, ROY is 20 degrees, as we can see there. Then SRO is 10 degrees, as we can also see there. And lastly, SZ is a chord that we have. Okay, so the first question is, we need to calculate with reasons the size of the following angles. So the first angle is angle S1. So let's go ahead and look. Here we have angle S1. Remember, when you look at your angle, you don't just stare at it and hope that you see the answer. You start asking yourself questions like, where is this angle? Okay, first of all, I can see it's at the circumference. So I'll try to relate it to rules about angles at the circumference that we know. We know, yes, the angles at the circumference, if they're supported by the same chord, that they're going to be equal. But unfortunately, as you can see, the chord, or the arc rather in this case, RZ, that is supporting this angle, is literally the only arc supporting this angle at the circumference. But we also know about the rule that states that the angle at the center is double the size of the angle at the circumference as long as they're supported by the same chord or arc. And I can see that over here. This is supported by RZ, but we also have another angle at the center supported by RZ. So if this is 20 degrees, it's double the size of this one. So that will therefore be 10 degrees. So that's what we have over there. Let me just put it in another color. So we have 10 degrees over there. And that is because the angle at the center is twice the angle at the circumference. Okay, so that is it for that question. And moving on to the next question. The next question, we have to find the size of angle R3. Okay, where is angle R3 first of all? So angle R3 is over here. So let's think about the things surrounding angle R3 that we can see. So I see parallel lines. You see these two lines are parallel. And then we have a line here, which we'll call our transversal, because that is the line that joins the parallel lines together. It goes from one parallel line to the other parallel line. It doesn't really join them. But you see what happens over here. So it means that we can actually look for fun angles here. And immediately we can already see that this forms a Z or an N. So it would mean that angle R3 should be equal to this angle, angle O1, which is 20 degrees. Okay, so that means that angle R3 is actually equal to 20 degrees, of course, because it's equal to angle O1. And this is because of, we have alternate angles. Okay, so alternate angles on parallel lines are always equal. Okay, another thing that you can do after telling them it's alternate angles is tell them the lines that are parallel. So as you can see, it was RQ being parallel to basically what they said. Okay, OY being parallel to RQ. That is fine to say. Just make sure you tell them that OY is parallel to RQ. Okay, so that is it for that question. Moving on to the next question. The next question, we have to find the size of angle P. So let's go ahead and see. So angle P is over here. So how can we actually find the size of that angle? Well, as you can see, it's taken up a really big space. So the best way to actually find it is using a shape like a triangle, or looking for, if you have a quad, okay? Because the triangle is not very helpful. So let's actually see. So you see, if you go like this and you try to draw a quad within the circle, which is a cyclic quad, do you see that we actually do have a cyclic quad? And what do you know about angles in a cyclic quad that are opposite each other? They add up to 180 degrees. So it means that to find angle P, you're going to have to take the opposite angle, okay, and subtract that angle from 180 degrees. So it means that to find angle P, or you can look at it like by saying 180 degrees minus this angle, since they must add up to 180 degrees. That is 20 degrees and 10 degrees. So it's actually minus 30 degrees. These calculations don't really mean that much, because when they see the answer, they will know, okay, you did that calculation and your reason will back that up. So it means that that answer there is 150 degrees. And that's of course because opposite angles in a cyclic quadrilateral are supplementary or add up to 180 degrees. Okay, so that is it for that question. And always just make sure that as you are working through these, be filling in the angles that you find, because it's going to probably help you with the next question. Okay, moving on to the next question. The next question is we need to find the size of angle S2. Okay, so angle S2, let's see. So this is over here. How can we actually find the size of this? So we can look at the angles that it is a part of. You see that together this create one angle, but that doesn't really help us to find anything. Let's actually try to look at it like this. It is at the circumference, right? So we can apply rules about angles at the circumference. However, the chord that is supporting it is this chord. And as you can see, that chord is not supporting anything else. So there's one rule that we always don't even think about when we think about angles at the circumference. And that rule is the tan chord theorem, because it relates to an angle at the circumference. Okay, it says the angle between a tangent and a chord is equal to the angle opposite that chord, okay, or supported by that chord. But do you remember that that angle must be at the circumference? So we can think in that direction. This is an angle at the circumference. This is the chord supporting it. So the angle between this tangent, okay, and that chord would be angle R4. And so it means that angle R4 would be equal to angle S2. So our goal is now to find angle R4. How can we actually find that? And now that I think about it, you see the mark allocations here is 4. So it's going to actually take you longer to find it. There's more steps that you need to take to find that. To find angle R4, do you see that we have a radius over here? If this is a tangent and this is a radius, they must be perpendicular at their points of contact. This is why it's important to fill in your information when you see it. So to find angle R4, you can say 90 degrees minus 20 degrees, because this angle R4 and angle R3 add up and give you 90 degrees since we have perpendicular lines here. Okay, so angle R4 is what we clearly have to find first. We say angle R4 is found by saying 90 degrees minus 20. And our reason is because the radius is always going to be perpendicular to the tangent at the point of contact. And therefore, it means that angle R4 is equal to 70 degrees. So now that we have angle R4, we can go ahead and find angle S2. So this is 70 degrees. And so the angle between the tangent and the chord is always going to be equal to the angle at the circumference that is supported by that same chord. So that is also 70 degrees. Okay, so we just have to write that down. Tell them that angle S2 is therefore equal to angle R4. And so that means that angle S2 is equal to 70 degrees as well. And this is because of the tan chord theorem. You don't have to actually write the full tan chord theorem. You can follow the reasons that they use in the memo. If they can use it in the memo, then you can use it. Okay, so that's because of the tan chord theorem. There we go. Okay, so that is it for the little bits of questions that they're asking. We have one more bigger question after this concerning this diagram. Okay, moving on to the next question. Then the final question in this diagram, and actually in question 8, yes, is prove that XRY is a tangent to the circle passing through RT and O. Okay, so we're going to have to look at this. They want us to prove that this XRY is a tangent to the circle passing through RT and O. So it means that we're going to have to sketch a circle here first and then prove that that is a tangent to that circle. So let me go ahead and draw that circle. Okay, so here's our circle. I tried my best to make sure that RT and O are on the circumference. Okay, So when we're looking at this circle, they want us to basically prove to them that this tangent is a tangent to this little circle that we have just drawn. So let us just think about the way that we can actually prove something is a tangent. If you want to prove something is a tangent, there are two theorems I can think about that mention tangents. The first theorem we have is that tan chord theorem, which we just worked with now. So if you ever have a tangent and you have an angle, right, between the tangent and the chord, and you have another angle over here, if this really is a tangent, right, for it to be a tangent, then the angle here must be exactly equal to that angle over there. The other theorem I can think about that mentions a tangent is this one, where we have a tangent to a circle, but in this case we'll have a line coming from the center of the circle, specifically a radius. We know that the relationship between a radius and a tangent is that it's always going to be perpendicular at the point of contact. Okay, that's if that is a tangent, you will notice that. So do you see the two theorems that you can actually work with to prove that this is a tangent? This is how you guys can be thinking about this grade 12s. When they ask you to prove something, you prove something is a tangent, you're going to have to think about theorems that relate to tangents. If they want you to prove something is a diameter, you're going to have to think about theorems that relate to diameters. Okay, so let's go ahead and see which one we can use. So because there are a lot of lines here, I would actually go with the tan chord theorem, just because, it just feels easier to kind of prove. So let's think about it now. This is R, T, and O. We are only allowed to use those points on the circumference of this circle because we want to prove that's a tangent to this circle. So we can look at it like this. The angle between the tangent and the chord in this circle, which is RT, right, is this angle 70 degrees. And the angle supported by that same chord in this little circle, this blue circle, that would be, because this is your chord here, so that angle supported by it is angle O2. What does that actually mean? It means you need to find the size of angle O2. And if truly angle O2 is equal to 70 degrees, then you have a tangent to this circle. So you see, these two need to be equal to each other for this to be a tangent. That's what we need to look at. So the goal is find angle O2. Okay, so how can we find angle O2? I just changed that because I don't like how they look the same. They're not supposed to be the same. So with that, what we can do here is, how can we actually find this? Okay, let's just see, what can we use in this situation? Well, I see other things that are equal to 70 degrees, but this one, it just seems too far to even help with this. So I'll leave that for now. I won't think about that. I see that this angle O2. So another thing you can do is, yes, we know it's at the center. Unfortunately, it is not at the center being supported by a chord. You see, if you look at the bigger circle, this is the full chord. Unfortunately, this angle O2 is only being supported by that little thing. Okay, so what we can do in this situation is, why don't we look at O2 as in what is it part of? Do you see that it's part of a triangle? So in this triangle, sorry about that, in this triangle, all you have to find is the angle T1. Okay, if you find angle T1, then you find angle O2. So now our focus is on T1. How can we find angle T1? Okay, perfect. Do you see that we have a chord in the bigger circle? And they told us that this, clearly we know this is coming from the center, always the center. So there is a line from the center that is going to the what of this chord. They told you that these two lines are equal from RT to TQ. They are equal. That's why those lines are there. So it means this line is going from the center of the circle to the midpoint of the chord. This is the converse of theorem 1, the first theorem you usually learn. And what that theorem states is, if we have a line from the center of the circle to the midpoint of the chord, okay, given that that is the midpoint, then it means that this line is also perpendicular to that chord. So we know exactly what T1 is. It's supposed to be 90 degrees. So let's go ahead and tell them that and give them the reason for that. So we're telling them that angle T1 is equal to 90 degrees. Angle T1 equals 90 degrees. And the reason is because of the angle, the converse really of that first theorem. But we can actually just write it out. So in this one, this is the reason, but I just realized we can actually start off by telling them that OT is perpendicular to this line RQ. We can first say that, and then this is really a conclusion to that. So OT is perpendicular to that line RQ. And so because of that, it means T1 is equal to 90 degrees, and that's our reason. Now that we have shown them that T1 is 90 degrees, we can go ahead and use that to find O2. So this is 90 degrees. We can use the angles inside a triangle. So the calculation for that can just be that angle O2 is found by saying the total angles in a triangle, 180 degrees, minus the angles inside. That's the 90 degrees and the 20 degrees that we're going to subtract. So minus 90 degrees, minus 20 degrees, and that's because of the sum of angles inside a triangle. So that is going to give us, you know, that 180 minus 90 is 90, 90 minus 20 is 70. So that is 70 degrees indeed. And because angle O2 is also equal to 70 degrees, then it means that it is equal to the angle between the tangent and the chord. Okay, the angle between the tangent and the chord really is equal to the angle supported by that same chord in this little blue circle. So let's go ahead and put that down. So the conclusion is that angle O2 is really equal to angle R4, and because they're both equal, we're concluding that. Now this theorem, it's not really, I can't just say because the angle between the tangent. It's really because of the converse theorem, okay, the converse of the tan chord theorem, because that's what we did. Instead of using the tan chord theorem, we actually did it backwards, because normally the tan chord theorem tells us this is a tangent, but in this case, we were trying to prove to them that this is a tangent. So the reason for this is because of the converse, okay, of the tan chord theorem. So that is what we have there. Okay, so that is the last question for question 8. Question 9 says, in the diagram below, triangle ABC is constructed so that BC, so this is BC here, is produced to D. Then DR is drawn with a point T on AC and R on AB. Okay. And then they tell us that CS is drawn. Okay, that's just the line there. So not that it's parallel or anything yet, but I say yet because it's probably going to be. We have a triangle. And then they tell us that CT is 12 millimeters. TA, as you can see, is 36 millimeters. SR, on the other hand, is 20. So that little thing is 20 millimeters. And then SA is 80 millimeters. Okay, the first question is to prove that CS is parallel to TR. So prove that CS is parallel to TR. Okay, grade 12s, with these questions, right? When you start seeing the diagram and you start seeing them explaining how certain lines are drawn and all of that, it is very helpful to become comfortable with the diagram. So before even scaring yourself with the questions, you can actually look at the diagram and figure out some things. This is just to calm you down in the exam so that you know what you're working with. Okay, so you just try to not take too much time doing that. Just look at it like, okay, I see a triangle and I see a line here. So they probably want some sort of relationship between those two lines. Maybe they're parallel or something like that. Okay, and I see another triangle here as well. You do these kind of things just to make yourself comfortable with the diagram and so that you're not too surprised by the questions. Okay, so the first question is to prove that CS is parallel to TR. Let's go ahead and look at that. So you know that we're not going to use fun angles here because they haven't given you any angles at all. We're just going to have to use the lines. And since we're going to have to use lines and you can see we have triangles, you're going to have to use the proportionality theorem. Okay, so if we can actually show them that the proportionality theorem is working here, then it will prove that these two lines really are parallel. Okay, let's just quickly go through that because I don't want to just assume that we're all clear on that. So we're going to look at a triangle, right? The proportionality theorem states that if you're given a triangle and one side, okay, a line is drawn parallel to one side of the triangle, then what this means is that the sides in this triangle are going to be proportional. So let's just call that EF. They're going to be in proportion. So that would mean that, for example, AE over AB, if you simplify that, it's going to be the exact same number or the same ratio as taking AF. Okay, so you see we took AE first, so we had to take A over AB. So you also have to take AF over AC. Okay, so it doesn't mean that they're the same in length. It just means that once you simplify them as a fraction, it will give you the same number, the same fraction as that one, because they're in proportion. Okay, so let's see if we can actually see that here. So do you see that they've given you some sides? So this is going to be so helpful. Let's just choose the sides so we can take over each other. How about we look at it by taking, we can go ahead and try taking CT, right, over CA. And the reason I want to take that full thing is because do you see that they gave us SA? Okay, they already gave us SA. You might as well just do that. And we can take it as SR over SA. Okay, so let's go ahead and see what that gives us. So we'll take them individually. Let's go ahead and start here. So I'm taking CT over CA, or let me just call it AC, of course, in alphabetical order. So that is CT over AC. And we're going to find out what that simplifies to. So that is 12 over the full length. Okay, so 12 over, this is 12 plus 36. If you add that together, 1 and 3, that's 4. So that's 48. So over 48. Let's see what that gives us. So this simplifies to, well, I know that 12 can be divided into 48. So once, actually only once, and this can go 4 times, so that's going to be 1 over 4 that it simplifies to. And then we can go ahead, I'm just going to write it next to it because it doesn't really need to be under. Then we can go ahead and also check those proportions in that order. So SR over AS, or SA. Okay, so SR over AS, and let's see what that gives us. So that is 20 over the full length of SA. I don't know why I wrote AC, which is 80. And as you can see, you know that if you obviously divide 20 can go into 84 times. So that is 1 over 4. Now, because we see that they end up being the exact same thing, it would mean that CT over AC is indeed equal to SR over SA. And so that means that these lines are parallel since their sides are in proportion. So therefore, it means that CS really is parallel to TR. And the reason it's parallel, well, it's really the converse of the proportionality theorem, but I don't like to use that word proportionality theorem. I like to use the meaning of it, right? So the proportionality theorem states that we have a line drawn parallel to one side of the triangle, right? But we were not told that these two lines are parallel yet. So instead of saying that, I can tell them that this line, right, instead of saying it was drawn parallel to one side of the triangle, I can say that this line divides the sides of the triangle proportionally. So that is the reason I'm going to use. So it's sort of the converse theorem of the proportionality theorem, but I'm just not using that word converse. Not really necessary, because I am still stating that converse relationship, really. Okay, so we are done with that question. That was for 3 marks. And moving on to the next question. The next question, 9.2, says it is further given that AR is equal to 2 over 3 RB. Okay, we need to just be putting these down. And they tell us that BC is equal to 2x. And CD is equal to this, also in terms of x. We need to calculate the value of x. Okay, let me bring the diagram down. So let's put down what they have told us. So they said AR is equal to 2 over 3 RB. Let's go ahead and fill that in. So this is AR. It is 2 over 3 RB. So 2 over 3 RB. They're calling it RB, so we might as well look at what else is, where is RB? Okay, so RB is here. You see RB. So that's going to be very helpful. Okay, and then they tell us that BC is 2x. BC, so here to here, is just 2x. And then CD is a half x plus 1. So half of that length plus 1. 1 over 2x plus 1. Okay. So since we know all of that, the question is you need to solve for x, so find the value of x. Okay, let's just look at this. Well, there's one thing we know now that I didn't even put down. You see, we've already shown them that these two lines are parallel. So we can go ahead and tell them these two lines are parallel. Now you can use the proportionality theorem on any triangle you find that include these two lines, these two parallel lines. So we previously used it here. But now, do you see there's another triangle that we have here? This one. And the reason we can focus on this is because you see most of the things that they gave us are part of that side. So how can we actually use this? Well, I see a very nice pattern going on here. You see they gave us BC and they gave us DC. So all we really need is to be able to find this. Can't we just use DC over DB and say that because we have parallel lines, that proportion should be equal to RS over RB. Okay, and the reason RB is going to be very helpful here is because they told us something about RB. They said that this little length over here is equal to 2 over 3 RB. Okay. But in order to actually use that, because you see that these ones are in terms of x, this one has a number, which is nice, but then this is in terms of RB, which is not very helpful. So how about we find out what exactly is RB? What is the length of RB? And we can find out that because of what they told us. Do you see that they told us that AR, right, that was equal to 2 over 3 RB. If they told us AR is equal to 2 over 3 RB, let's find out exactly how much AR is. See, look at this. They told you that SA was equal to 80 millimeters. And you know that part of SA is SR. That is 20 millimeters. So how much is this? What is the length of this? This would be 60 millimeters. So because 60 and 20 would give you the full 80. So they told us that AR, we just calculated that AR is equal to 60 millimeters. If you like, you can show them the calculation, but you see, we can just look at that and actually subtract. We don't really need a reason for subtraction because subtraction is more like a fact than a theorem. Okay, so since we now know the size of AR, and they also told us that AR equals 2 over 3 RB. So in place of AR, why don't we just put the 2 over 3 RB? And we're saying that that is equal to 60. And now we can actually just use this equation to solve for RB. So to solve for RB, you see you have to get rid of the 2 over 3. So we can divide both hand sides by 2 over 3. So therefore, it means that RB would be equal to, 60 divided by 2 over 3 is like saying 60 times 3 over 2 because we tip and times when we divide. And so if you're dividing, you can look for what you can cancel across. Because with Euclid, you don't really need a calculator though. So 60 and 2 have 2 in common. 2 divided by 2 is 1. 60 divided by 2 is 30. So this is actually 30 times 3, which is 90. So now we know that RB is equal to 90 millimeters. Okay, we just use that information they gave us here to solve for RB. And now that we know what RB is, our job here becomes so much easier. So this is 90 millimeters. And now we can go ahead and use this proportionality theorem over here. So remember, because they already gave us 20 and they also gave us DC, we can tell them this. Because these two lines are parallel in this red triangle, we are going to tell them that DC, right, that side over DB, we can call it BD, it should be in proportion with RS over, I'll just call it BR. And the reason, of course, is because of the proportionality theorem, but I like to say because of the line parallel to one side of a triangle. Okay, so we have that. And now we can go ahead and substitute the values that we have in these proportions. So DC is what? DC is a half, so a half x plus 1 over BD. Now BD is the full length, so from here all the way to there, we can actually just calculate what exactly that is. So BD is equal to that half x plus 1 plus the 2x. So that's the whole length of BD. So that is plus 2x. We know that a half plus x, or you can look at it as 2 plus a half. It's like a mixed fraction. So multiply the whole number and the denominator, which gives you 4, and then add the numerator, which gives you 5, and the denominator must stay the same. So that is just 5 over 2x. And then you still have the plus 1. So that's going to be the length of BD. Okay, I decided to put that there, and I'll just put this one here. We can work on this now. Okay, so we're saying that DC, which we have, over BD, which we now found to be 5 over 2x plus 1, that should be equal to RS. And what is the length of RS? RS is 20 units that we had there. So that's 20 over RB or BR, which is the full 90 millimeters. So 90 then millimeters. Okay, so do you see that this is an equation? And you just have to simplify because you have a fraction and an equal to sign. Just cross multiply. So we're going to cross multiply. Remember, you have 2 terms here and 1 term. So this 90 needs to multiply to this and that. 90 times a half, that's just half of 90, which gives you 45. So that's 45x. And then 90 times 1 is still positive 90. And this is equal to, cross multiply, going to say your 5 over 2x times 20. Let's just see what that gives us on the side. So times 20. I see that across we have common factors. So divided by 2 is 1. Divided by 2 is 10. So that leaves us with 5 times 10, which is 50. So we have 50x there. And then we have the 20 times 1. Okay. And 20 times 1 is just positive 20. Okay, so this is a linear equation. We just have to solve for x. So because this is smaller, I'll take it over. So that's 50x minus 45x is equal to 90. And then the 20 comes over and becomes a minus 20. 50x minus 45x is finally just 5x is equal to 90 minus 20 is 70. And then divide both sides by 5 to solve for x, and x is therefore equal to 70 divided by 10 is 7, so this is just twice the size, so it's 14. So it's equal to 14, and that is your answer for x in this question. Okay, so that is that question. It was a little bit long because it's like a whole 6 marks, but it's good for practice. Okay, so that is it for that question, and that is question 9. We move on to question 10, which you can see is a proof. We're on question 10, and 10.1 says, in the diagram below, we have triangle ABC and triangle DEF are drawn such that we have angle A being equal to angle D. Okay, so these two are equal already, and angle B is equal to angle E, and angle C is equal to angle F. Okay, so these are things we don't have to prove. It's things that have already been given. So you need to prove the theorem which states that if two triangles are equiangular, then the corresponding sides are in proportion. That is, AB over DE must be equal to AC over DF. So we can just focus on that part only, okay? We don't have to prove that this is also equal to BC over EF, okay? We just have to focus on what they told us to prove. Okay, so one of the proofs that I already have on my channel, but I will still explain it in this video. So 10.1, okay, we have in this diagram, how do we actually prove this? Well, with this, let me actually just explain the idea behind it. With this, should I say it's kind of like the proportionality theorem? Because what we're really just doing is we're creating another version of this triangle, right? Another one of that triangle. And we're sort of actually picking that up and placing it on here. And what we're trying to prove is that AB, like they mentioned, over DE, okay? And do you see that the equivalent or the thing that is equal to DE here in this blue triangle would be this little thing here? We're trying to show them that AB over that little thing is equal to AC over, and they say DF. this part, which is really just this little part in our triangle. So that's what I mean by it's kind of like the proportionality theorem, really. Now, for us to do that, we first of all need to have points here, right? And we're going to call these points two different things. I'll just choose PQ just because they're very different from every other letter that is here. Okay, we're going to call those PQ. And the first goal, in order for us to actually do this, aka prove the proportionality theorem indirectly, right, is we are going to just have to, first of all, show them that these two lines are parallel. If those two lines are parallel, we can just use it. So it's not really proving the proportionality theorem, it's using the proportionality theorem on this. Okay, so that's what I mean by that. So the first thing we're going to do is we're going to put down these points. So you're putting it, I should have left that there. Yeah, we're putting it in a way that these two are equal. So we are drawing down point P on AB in such a way that AP is exactly the same length as DE. And then we're putting down a point Q on this line AC in such a way that AQ is exactly equal to DF. That's what we're doing in that part. So we're first going to go ahead and write down everything we are doing. Okay, so now that we have done that, the next thing we're going to do is actually join these. So we're going to join these two together. I'll just create a construction line. Okay, so that is it for the construction. And now we can go ahead and prove. Okay, so what we're trying to do is just show them that these two lines are parallel. So we're just focusing on this as a whole. Then we'll include that one afterwards. So how can we show them that these two lines are going to be parallel? Well, do you remember that they told you initially that angle B is equal to angle E, right? So the goal here is if we can show them that this one is also the same thing, then do you see that you have corresponding angles? And corresponding angles will always lie on parallel lines. So that's how we're going to do that. Okay, let's go ahead and start with that. So for us to actually show them that those two angles are exactly the same, we are going to focus on these two triangles now. For us to show them those angles are the same, all their corresponding angles are exactly the same, we can show them that these two triangles are actually congruent. So that is our first goal. So let's go ahead and draw or write down these triangles. Let's introduce the triangles. So we say in triangle APQ, and the second triangle that we have is DEF. We are going to try and prove these two triangles are congruent. Okay, so let's look at these two triangles and let's just see the things that are equal. So first of all, we see that AP and DE are exactly the same. And they're exactly the same because of our construction. So we can actually tell them that AP, first of all, is equal to DE, and that is just by construction. You see that we drew that point P in such a way that AP was equal to DE already, okay? So by construction. Okay, we have one side being equal, that's great. Then you see that we have these angles being exactly the same. So we can also tell them that angle A is equal to angle D. But this one is not by construction. We didn't cause this. This was something that they told us initially. So we can tell them that this is just given. Okay, so given. And remember, that's an angle. So it's a given angle that we have there. And then we can also see that in these two little triangles on top, AQ is equal to DF. So we can put that down as well. So AQ equals DF. And the reason for that one is not given. We caused that to happen, okay? That was by construction. So again, we'll use this exact same reason. That is by construction. And now you see you have three things already being equal in these two triangles. So it means, therefore, that triangle APQ really is congruent to triangle DEF. And the reason for this is a side, this is an angle, and this is a side. Okay, so you can tell them it's side, angle, side. That's the reason. Okay, now that these two triangles are congruent, so in other words, exactly the same, their corresponding sides and angle are all equal, it means now their angles are also equal. So this means that this angle over here, that P, but we'll call that APE, is equal to this angle over here. So we can conclude now. Tell them that angle APE is finally equal to that angle E. Okay, so angle E. I realized that I called this E, it should be Q. Sorry about that. So that is APQ. Okay, that it's equal to angle E. Okay, so now we know these two angles are equal. But here's another thing that we need to take note of. Do you remember we said now that these two are equal? But initially we already knew that angle B was equal to angle E. So we're going to tell them that. Tell them, but we already knew that angle B was equal to angle E. So what does that mean about angle APQ and angle B? That would mean that those two angles are exactly the same as well. It means that angle APQ is finally also equal to angle B. And this is what this means in the diagram. Because APQ is equal to angle B, do you see what we have now in this triangle? We have corresponding angles. These two are exactly the same. Okay, so if you have corresponding angles, what does that mean about this line PQ and BC? It would mean that those lines are parallel. Okay, so that was the whole goal, to get these two lines to be parallel first. So our conclusion there is that PQ is parallel to BC because of corresponding angles. Specifically, the corresponding angles are equal, the corresponding angles. Okay, so now that they are parallel, now we can go ahead and start working on this. So tell them that they are parallel, and now we are going to have to use the sort of proportionality theorem. So this is where you need to now focus on what they told you. So it's not as if it's always going to be exactly the same. And that's why it's a good thing I'm actually working on this now. It's not always going to be the same because sometimes they play around with the way that is written. Okay, so with this, we're saying AB, right, over DE. Now remember what the equivalence of DE is in this diagram. That is AP. So now you know what you're supposed to be trying to take, the proportions you're supposed to be taking. They say that that should be equal to AC over DF. And the equivalence of DF here is AE. So that's what we have to actually show them. We have to show them that because these two lines are parallel, it means that AB over AP is equal to AC over AQ. Okay, so that's what we have there. And we can go ahead and say that this is because of the proportionality theorem, or really just because we have a line parallel to one side of a triangle. You could just say side of triangle. Okay, so side of triangle. Okay, so now that we have that, here's the thing about this. So how we tried to make sure that this is really just, this construction we have made is really just this triangle fitting onto this triangle. So that's where this is going to come in. Because we already know that these sides are equal, because we already know that AP is equal to DE and AE is equal to DF, we're just going to replace them, okay, with these in our proportions. That's really what we're doing now. So I'll tell them, but I already know that AP equals DE and AQ equals DF. And because we know that, we can actually substitute them here. So AB over, and then I see AP, but we told them that we knew that AP was already equal to DE by construction. So DE, I replace that with DE, is equal to AC, and then in place of AQ, we know these two are already equal. So that is equal to DF. And do you see that we have actually proven that AB over DE equals AC over DF? And that is the proportionality, well, not really, that is the proof for equal angular triangles have their sides in proportion, okay, their corresponding sides. So that is it for that first part of question 10. And then we move on to 10.2, which is on a diagram. Okay, we have 3 questions here. Let's go ahead and start with 10.2.1, but let's read the information first. Okay, 10.2 says, in the diagram below, we have a diameter EMA, right? Diameter of a circle with the center M. So they already told us this is the center. That what it does is that it bisects FAB. So it bisects this bigger angle. Remember, if a line bisects an angle, it means that it cuts that angle into two equal parts. So these two are equal already. We know that from the beginning. Then they tell us that MD, right, is perpendicular to the chord AB, which is no surprise because it's going from the center of the circle. Okay, so it's perpendicular to that chord AB. And then they tell us that ED produced meets the circle at C. That doesn't seem that important, but ED produced meets there. And then chord CB, so CB and FE are just drawn. Okay, so those are just chords that we have there. Okay, so the first question is to prove that triangle AEF is similar to triangle AMD. So let's look at those triangles. So AEF, first of all, is this triangle A to E to F. So AEF must be similar to AMD. So AMD. So I'll just mark that in blue. Okay, so as you can see, they didn't give us any, sides, the length of any sides. So we just have to use the angles that we have here. So from the beginning, we can already see two angles in each triangle that are equal. So this, because of, that diameter bisecting that bigger angle, that angle A2 is already equal to A1. We can see that already. And, it's better to figure it out here before actually writing it down. You can actually be writing it down, but it just saves time and saves you writing things that are not needed. Okay, so the next thing I see is, yes, this is a diameter. So since it's a diameter, it means that the diameter is always going to subtend or support a 90-degree angle because of angle in a semicircle. So that's 90 degrees, but this is also 90 degrees. So do you see that you have two corresponding angles being equal? So it would mean by default that the third angle in each triangle should also be equal. So that one is not so complicated. It's actually quite simple. We just need to now write it down for them. So let's go ahead and name the triangles. So in triangle, and they already named it for us. So AEF and triangle AMD, that this is what we have. We first of all were told these two are equal. Well, we're not told, but we know they're equal. So angle A1 is equal to angle A2. And that's because that, or we can just say EMA, bisects FAB. Okay, so when it bisects, it cuts it in half into two equal parts. And then we can tell them that angle F is equal to 90 degrees because of angles in a semicircle. Okay, so we can put that down, angle in a semicircle. And so because it's equal to 90 degrees, you already see that D1 was already equal to 90 degrees. So that therefore means that angle F is equal to angle D1. So this is our main conclusion. We're just saying that these two angles in those two separate triangles are equal. Then the third angle that we have is angle E1, which is by default equal to angle M1 because of really the sum of angles in a triangle, or you can call it the third angle in a triangle. Okay, so this is what we have. And since we have these three angles equal, it proves that triangle AEF really is similar to triangle AMD. And our reason, of course, is angle, angle, angle. Three sets of angles are equal in each triangle. Okay, moving on to the next question. The next question, 10.2.2, says, determine the numerical value of AF over AD. The numerical value of AF over AD. So let's just get rid of things we don't need. We don't really need these lines. We just need to know the angles that are equal to each other. So we know these two angles are now equal. This is equal to this. That's all we really need to put down there. So these two angles are equal. And those are 90 degrees. Okay. So they want us to find the numerical value of AF over AD. AF over AD. So AF is here over AD, which is here. Okay, those are the sides in the triangles that we just showed them are similar. So the way I'm thinking about this is really the way equiangular triangles work. Okay, we don't have to get into that kind of detail because these sides, right, are part of the equiangular triangles. We can actually try and use them. So let's go ahead and get the proportions based on this. So what I mean by that is because we know that these two triangles are similar, what we can actually conclude from this is this. So you can take, because they mentioned AF, I'm going to use AF, right? So you see I use the first and the third letter here. Here I must also use the first and third letter, and that actually goes in order, like the way they asked it here. We know that AF, right, over AD, because it's in proportion, it should be equal to EF, for example, over, so I took second and third, you must take second and third here, over MD. So it's equal to EF over MD. And that is also equal to, the only ones I didn't take is AE over AM. So AE over AM. So that's first and second letter. So they're in proportion like that. So because this is what we're trying to find, why don't we just check if we can somehow find a numerical value of any of these other sides? So we're looking at EF and MD. So EF and MD, let me just erase this. I'm not really looking at that yet. EF and MD. And we're also just looking at AE and AM. So AE and AM. So that is AE and AM. So the shorter one. Okay, by already drawing that, I can already see something here. I don't actually need MD and FE. They're not so helpful. Here's the thing. Do you see that AE is a diameter? And from the center to the circumference is AM. Center to the circumference is ME. So why don't we just associate a specific letter to the radius? Why don't we just call MA, for example? Let's call that X. If that's called X, because this is also a radius, it should be X as well. So I'm going to to do this one, I'm going to actually say, let AM be equal to X. Because it's equal to X, these two are equal. So I'll tell them that AM is equal to EM because they're both equal radii. So AM equals EM. Okay, because of radii, I don't really need to say that they're equal, just radii that are equal. And so therefore, it means that if you were looking at the diameter, okay, that's AE, that is equal to, if you calculate it all together, that's 2x. We add them. So let's just show them now. That it means that AE is 2x. So here's why this is so helpful, why this line is very helpful. Because we were looking at this side AM and that side AE, those were part of the two similar triangles that we have. And we now have values or letters associated with their lengths. What we can actually do is use that here. So instead of using these two, we don't need that. We can just use this instead. So we're going to tell them that, okay, this means that we're going to say AF over AD is equal to AE over AM. And this is of course because our triangles were similar, so their sides are in proportion. So you can tell them similar triangles, okay? And so I don't need this part. That was just to figure it out. Usually I'll write that in pencil. So this is what we have. And since we have this now, we can go ahead and start substituting. So the whole goal is to find out what AF over AD is. So AF over AD is equal to, AE is what? It's 2x. And AM originally was x. So that's over x. Do you see now that if you simplify this, your x would cancel. And so that concludes that AF over AD is equal to 2. That's the numerical value of AF over AD. Okay, so that is for 3 marks. And then we move on to the next question. Okay, so we are on the last question and it says, prove that AD squared is equal to CD times DE. So with this, we're always just going to mark out the lines that they mentioned so that we can figure out how that, can get to this. So AD, CD, and DE, let's go ahead and mark them out. So that's AD, CD, and DE. Okay, so when you look at that, that just creates a Y. But also just remember that we have AD squared, right? So that was that AD squared should be equal to CD times DE. Since that is the case, let me actually just pull this diagram down. Okay, so when you look at this, it creates a Y, not really a full triangle. However, it seems as if they're using this triangle here and another triangle. So the only triangle that includes DC would be this one here. So let's look at how that is going to work. You see, with the AD squared, I wanted to say maybe they're using Pythagoras, like the actual Pythagoras, the C squared equals A squared plus B squared. But the thing about Pythagoras itself is you should see a plus or minus somewhere, okay? Should be a sign there to show that, okay, this was possibly Pythagoras being used. Sometimes it's not like that, but in this case, because it actually is focusing on two triangles, they probably just didn't. They probably used something that was equal to AD. So can we actually see a line that is also equal to AD? Well, do you see here now that if you take this line from the center of the circle to this chord, do you see that it's perpendicular to the chord? So what else do we know about that? That it would bisect the chord. So that's probably something they used. Okay, I'm going to actually just put it down because I actually do think they use this. However, normally I would not recommend you just start writing things down, or like try to figure it out first, then, write it down. So, okay, if these two are equal and we still know that they are using this other line, then it probably, yes, it definitely means they're using this triangle. I'm also realizing now that these two triangles, do you see that these two angles are vertically opposite each other? So because they're vertically opposite each other, they are equal. So we will just have to find their other angles, and I can already see now that they are equal. Do you see that this is an angle at the circumference? Let me just get rid of these. Do you see that we have an angle at the circumference, A2, being supported by arc BE? That angle would be equal to this angle at the circumference, C, also being supported by the same arc. So you can see those two angles are equal. And because this is a bow tie theorem, you can also look at it the other way around, that E2 should be equal to angle B because they're also supported by the same arc. So those two are also equal. And we have vertically opposite angles, so they definitely use that. Okay, so let's go ahead and start off this story by actually showing them that MD, the line from the center to this chord, that it actually is bisecting that chord. So I'm going to tell them that AD, first of all, is equal to DB. And that's because we have a line from the center, okay, perpendicular to the chord, that bisects the chord. Okay, line from center perpendicular to the chord. So because those two are equal, you can call DB AD. That's probably where they got the AD squared. So the two triangles we know we are now using are these two triangles. This triangle over here and this triangle over here. So for us to properly use these two triangles, what we're going to go ahead and do is to prove to them that these two triangles are similar, because we can't just go start using their proportions without even showing them that they were actually similar. So let's go ahead and prove that. So we'll say in triangle, and beforehand already figure out how they are similar. You now know that this A2 is equal to angle C because of that bow tie theorem. And you also know that this E2 is equal to angle B. So we're going to have to look at it in order. And you know that this one at the, these two are equal already. So this is going to work like this. You can call this DCB. So I'll call that blue one DCB. And the second triangle is triangle. Let's also name it in order. You see, we started from the D, right? And we're going to the angle, this angle at the circumference. Now the angle at the circumference of the red triangle is angle A2. That's the one that is equal to angle C. So we have to call this DAE. So DAE. Okay, so now that that is there, we can go ahead and start proving. So we can tell them that these two are equal. So angle C is equal to angle A2 because of angles in the same segments are equal. And I can also see that I also take these two that are equal. So I'll tell them that angle B is equal to angle E2. Same reason, angles in the same segment. And the third one, honestly, at this part, you can just be lazy about this part, the third one, because it's not really necessary to now say because they're vertically opposite. You can just say third angle in the triangle. Okay, so we'll tell them that angle D4 is equal to, now properly name this triangle because it has two parts. You can't really just call it angle D. You have to call it angle ADE. So that is equal to ADE. Because those three things are equal, we can therefore, well, that is because of the third angle in a triangle. And now we can conclude that these two really are similar. So triangle DCB is similar to triangle DAE, okay, because of angle, angle, angle. Three angles are equal in these triangles. Now we can go ahead and use their proportions. So remember that we had AD squared, but we could see clearly that they probably replaced AD with DB because those two are equal. So the sides that we're going to have to focus on using is really the sides that we see here. If you see AD squared, we're going to use AD, and in the blue triangle, we'll use DB. Okay, so what I'm trying to look at is where is AD in our proportion? AD is here. So I have to say AD over, now it has to correspond in that second triangle. So if I take AD, I must take CD. So over CD is equal to, so how do I know what else to take? Well, you have to take a side that is included in this equation that they presented to you here. So we have CD already, so we can't take that. We can focus on taking DE because we don't have that. So DE, where is DE in our triangle? Well, we don't need to look at it in the triangle. We just need it here. DE is here, DE, first and last letter. So you must also be consistent here. Take the first and last letter as well. So over DB. And we actually have what we need now. Okay, so you can go ahead and, well, let me not just go start cross multiplying. Do you remember that? You see you have AD, we need AD squared. We have DB here. This is DB, right? This line here. Do you remember we have already proven to them that AD is equal to DB? We knew that because we had AD squared. They must have gotten an AD times an AD. So they definitely got something that was equal to AD. So because that is equal to AD, we'll tell them, but we already knew that DB was equal to AD. So in this, we're going to just replace that there. Also, we should have a reason here. The reason for this is similar triangles, but I think you actually just supposed to tell them the triangles that are similar, but you know, we already spoke about that there. So AD over, now in place of DB, we're just going to replace that with AD. That's all that we're going to do over there. So AD over CD is finally equal to DE over, and in place of DB, we call that AD. So we're almost there now. You see, they had AD squared. So it means that they just cross multiplied. So we'll say the AD times the AD, which gives you AD squared is equal to, and then the CD times the DE, which is CD times DE. And that's exactly what they have. Okay, so that's exactly what they asked us to prove. AD squared equals CD times DE. Okay, so there we go. You see that the whole thing with this part of Euclid is, first of all, spotting the lines they're speaking about. When they have something like this, it could be various things. It could be the theorem of Pythagoras. It could be the other theorem of Pythagoras, this one, okay, which is still in textbooks, okay, but I haven't seen it in a while in exam papers, really. It could be this one as well. And it could also just be a case of two lines being exactly the same. And so they became that line squared. Okay, so that is it for this paper. All the best metrics for prelims, and I will see you guys in the future videos. Bye for now.